Hi guys, today's lecture is about optimal control system. So why do we need optimal control? Okay, so variety of difficult real life problems can be formulated in the framework of optimal control. So the real problems can be brought into the optimal control framework because it has state and control bounds. So since it has a bounding nature because it ensures stability, so it has state and control bounds that can be incorporated in the control design process explicitly. So we have state and control bounds. So what is the meaning of state and control bounding? This is a state variables. So this is the control variable. So we have the opportunity to bring the state variables and the control variables to be bounded. So this is the plus in this. Next, incorporation of optimal issues lead to a variety of advantages like we always make a system, or if you want to go for any industrial process means we always go for minimum cost, maximum efficiency. So these are the main target for us for any industrial process or any business. So in that case, you need to go for optimal control system. And the main thing is the trajectory planning issues can be incorporated into the guidance and control design. So let's take one system. So the system transfer function is G of S. Okay. Then we can measure it, and that could be given to the optimal optimization. Then that is, and then here you have a reference value which is plus, this is minus, then from that it is given to the system. Okay, this is one case. And then you can take the same, and here also you have optimal control. In this you have to give the objectives, so it works on this objective, then based on the objective a reference is created. So you have a this trade-off between this, and finally the process will be controlled. This is the basic thing. Okay, then in optimal control formulation, the optimal because how do we frame the, what is the framework for this? So for that we have to we should have to follow certain things. One is we have to create a performance index, so that has to be framed and it has to be followed, that is optimized. Then this is the first optimal control formulation. Second formulation is we have to give appropriate initial and final conditions. Okay, so that has to be given. So for that, that leads to hard constraints and soft constraints. Okay, soft constraints it can be eradicated, or but hard constraint has to be followed. Okay, then third one is you have to give the path constraints. So in path constraints, this involve state constraints and control constraints, and then system dynamic constraints, which is non-linear. Okay, so first you have to frame the optimal control formulation. In that formulation, the first and foremost thing is you have to frame the performance index. Then you have to give the appropriate initial and final conditions. So that is hard constraint and soft constraint, but it has to follow this, or it may not be possible, or it may be possible that is soft constraint. So you have to give the constraint. What is the initial and what is the final condition? And then you have path constraints. So one is system dynamics, which involves, suppose if the system has nonlinearity, you have to inform that that is a constraint. Then you have state constraints, and then these are the variables to be controlled, and then the control variables. So these are the control constraints. So to frame the optimal framework, we have to follow this. Okay. Next, what is optimal control problem? So first we have to we have to find out the control law. Okay, we have to find out the control law, and then the control law should be applicable for one system. So this is a state space approach, function of state variables, input variables, and this is the input control variable. So this is state variable. So the system is dependent on, what's the function of state variables, control variables, and the time factor. So you have to determine the control law, and then the control law should follow the admissible trajectory. So this is the objective function. So the objective function could be anything. Okay, so optimization problem means you have to maximize the, so this is my objective. You have to substitute so that this value will be maximum. If it is minimum cost, you have to reduce the value. So you have to either maximize or minimize. So that is your objective. And then it should be subjected to constraints, hard constraints or soft constraints. And then it has to follow the variables. So this is how, or these are the components of optimal problem, optimal optimization problem. Okay. So again, those three components. So input data, objective functions, and constraints. So these are all very, very important so that the optimal control system will be so effective. Okay. So these are the basic five control problems. So terminal control problem, minimum time, minimum energy, regulator, and tracking. Okay. So the first one is terminal control. Example is, for example, if you want to, if you want to land it properly, so that is the automatic aircraft landing system, whereby the optimal control policy is focusing on minimizing error. So while it is landing, so this state, because this landing explains what the state variables like how much should be the angle, or what is the velocity, or what is, because while it landing, it should not have a friction, or it should not produce noise. So those are the variables. So that variables, you have some constraints for the variables also, and then the controlled variable will produce that too. Then when you compare, you will have some error. So that error has to be reduced. So you have to concentrate on minimizing errors on the state vector, on the state variables at the point of landing. So this is one example for terminal control. So this is used to bring the system as close as possible to a terminal state. What is this terminal state here? Landing. So you have to bring the system so closer to landing, or in what way? By minimizing the error. So this is your terminal control problem. The next one is minimum time control problem. So whenever you do any control action, make sure that it has taken the shortest time. So it will reach, so this is my target, that is landing is my target. So try to reduce the time, shortest possible time, then only the people will prefer the flight. So always go for it. So shortest possible time to reach the terminal state. So this results in a big bang control policy, because you set the control value to the maximum initially, then switching to minimum at some specific point of time. For example, in the case of a car journey, the driver keeping his foot flat down on the accelerator for the entire journey means, except at the terminal point, he when he brakes as far as possible. So in this case, he keep on increasing. So in that way, your value will be changing. So you have to concentrate on this big bang. But main thing is to reach this terminal state, how much time it has taken. Okay, that particular control system. Then the minimum energy control problem, so minimum investment. So this is used to transfer the system from an initial state to final state. So control is, we have one initial state, then we have to make the system to do the product to final state. So during this journey, the expenditure of control energy, the control effect, computations, everything should be minimum. So that is called as minimum energy control problem. We always use this for satellite control. Then the regulator control problem, with the system initially displayed from the equilibrium, because it is at equilibrium state, but when initially displaced, it will return the system to that state in such a manner that it has to minimize the given performance index. So what, for example, if the time is minimum objective function is given, so it has to, from the stability, it has to displace, and it has to be it will be returned back to the system with minimizing the performance standard. So this is called as a regulator control problem. Then the tracking control is, it has to keep on watching the state variables, got the state of the system to track as close as possible. Suppose if you give a trajectory like this, so here suppose this is your flight, so it has to follow. So suppose if it goes like this, so immediately the people closely watching this, there is some deviation, so they watch this and make the flight to move on this track. So you have to watch this as close as possible to minimize the given performance index. So this is called as a generalization of this regulator control problem. So these are the different control problems for a optimal control system. Then we have to discuss what is performance indices. Okay, the performance of any system is measured with performance index. So how do you measure the performance? With respect to the performance indices. Okay, the performance of a control system can be sufficiently specified in terms of settling time, less settling time, less peak overshoot, and ESS should be very less. So these are the general thing. So how do you measure the performance? By setting the performance index. So you have to say that this error should be 0.001 or 0.04. So this is the criteria you set. So that is your performance index. So now you have to prepare a control system so that the control system produces error which is 0.004. So that's why we are saying that the performance of the system is measured with the performance indices. Okay, this is one such performance index, and we know that ISE, integral square error. So let's see that. What is that? And in the integral square error is equal to, this is 0 to infinity, and E square. Okay, so this is the integral square error. So this should have the minimum value. Okay, but how do we do that? So for that, since the optimal control system is to find out the control law. So let me change this to a control law. So this is my control law. So how do we do that? So we can have J equal to, this can be splitted into U transpose of T into U of T. So when you multiply these two, you will get U square function, U square dt. Okay. So here, so J is equal to, I mean, this is the objective function. So it is U in 0 to infinity or to integrate, and then U transpose of T into U of T. But how do we should have a tuning parameter so that when you adjust the tuning parameter, this J value will increase for minimum time, minimum cost, and then the J value will increase. So this is the J value will decrease for minimum cost and minimum time. J value will increase for maximum profit or maximum efficiency. So you should have a tuning parameter. That tuning parameter is called as some matrix or value. So the nature of R is, it is a matrix which is diagonal matrix. Okay, it will have some value x1, x2, x3. The other values are 0, 0. Okay, so that if you change the values, if you change the value automatically, because this will not be changed, because this will give you that error value, so that your performance criteria is reached. So R is a diagonal matrix which is varied to control the performance index into minimum or maximum. So this is how we use optimal control performance criteria. Okay. So the next one is, so in that performance indices, quadratic performance indices is the common one we use in optimal control system. So let's see how to do that. So if the state and control variables in equations are squared, then the performance index become quadratic. So already we have discussed state and the control constraints, because any system x dot of t is a function of state, input, and time. Okay, if these constraints are squared, then we can say it is quadratic, the second order. So quadratic. So the, if your constraints, or if the control variables x and u as a control variables, x is a state variable, if they are squared in the equations, then that performance index is called as quadratic. Okay, then advantage of quadratic performance index is that it is for a linear system, it has the mathematical solution. So that mathematical solution is u of t equal to minus k. This is a control law, because this is a feedback, so this is minus control law. So this is directly proportional, so we can say that it is a linear system. So let's see what is quadratic performance index. So already we know that this is the objective function. Okay, so we have, because the integral square error should be minimum, so we can say that t naught initial time to this particular time. Okay, so in this we can have that some function, some state vectors. So u11 x1 square, because it should be quadratic, so the variable is squared, because x is the state variable. So it has 2 or 3 state variables. Okay, for example, if you take car, the state variables are displacement, then velocity. See, these are the state variables. So you have to select the state variables. So q1 is a coefficient, so one state variable, another state variable, and we'll have one more state variable, x3 square. So the state variables are squared, so it becomes quadratic criteria. Plus we have control variables also. That control variable we can name it as r1, and then this is u square. So since you have the square of these things, so we can name this as a quadratic performance criteria. Okay, then we'll split, we'll do some small adjustments. So J equal to, I'm going to split like this. So this is integration T naught to T. So here x1, x2, and x3. Okay. So here this is q11 0 0 0 q22 0 0 0 0 q33. Okay. So if you multiply this, you will get this expression. Then you have x, so because x1 square, so x2, x3, because we have seen previously this transpose, this is normal, in between you have a matrix. Okay, that is a performance criteria. Plus we have to do for control variables. So u separate or u transpose we can take. Here we have one matrix R and U. Okay, so this is ET. Okay, so this can be written as X transpose, because X transpose is Q, is the constant matrix or diagonal matrix, and then X. Okay, plus this one is U transpose or U. So that's all. This is your quadratic performance indices. So how does it work? You have state variables, state vector, and input control input vector. So the same thing is splitted into like this, same thing, but here you have a constant value. You keep on changing the value, keep on change R and keep on changing the value of Q. Automatically J will be affected. So it depends whether do you want to increase J or do you want to decrease J. So that is dependent on this. So based, first fix the criteria, fix the performance indices like minimum ISE or minimum settling time or minimal overshoot or maximize the profit or maximize the efficiency. So like this, fix the criteria and measure the state variables and measure the control variables, and in between you insert one matrix. So keep on changing the matrix till you get that required J value. So this is how it works. Okay, so we can have that optimal regulator. This is the control system. So as we have seen already, this is the system x dot, this is state matrix. I mean, this is state matrix, a state vector. This is control input. So this is control input vector. Input vector is B, state vector is A. Okay. And then we have already seen that U equal to minus Kx. So this is the variable, state variable that is measured using sensor. Then here it becomes minus Kx. Okay. So that is here U. Then input is 0 because you should have U equal to minus Kx. So that is given to this. And then finally, you have this C vector. This is also output vector. So C x we used to say. Okay. So we can write the system as x dot equal to ax plus b and y dot equal to cx plus du also sometimes you have, but this is 0, then better we don't have this. So this is state vector bu. This is input vector. This is output vector. So these are the vectors. So if you apply this, automatically the system will be under control because we have already given the optimized performance indices, and we have selected the quadratic performance criteria, and we have taken some matrices values. If we keep on changing the values, the system performance will be maintained. Okay, so one such regulator is LQ, the famous one, linear quadratic regulator. So we know that this is the function, this is the, so I have to this is objective function. I have to minimize this. I have to give minimal control law to maximize the performance. So I have given the initial conditions and then some constraints also I have given. So this is the normal equation. So here we are going to use the objective function as Hamilton-Jacobi function. We are going to use this function. This is a famous one. Okay. Then in this equation, I'm going to substitute the system. So the system is x dot equal to ax plus bu, and then we know that the quadratic performance criteria, we know this. This is the matrix, we are going to work on it, and then that j has to be substituted here. So here this is our function. This function has to be minimized. Okay. So how we are going to relate these two? So here for that, first we have to take the function. that function is x transpose px. So P is a new matrix, symmetric matrix. Then take the derivative. So you will get x of t as it is, then dou by dt of px. Okay. So suppose if you differentiate with respect to x, then this is the output 2px. And if you take the transpose, then it is 2x transpose p. Okay. So because I'm going to substitute in this, so we have to do these things. And finally substitute in that equation. So here this is the quadratic performance criteria, and then you substitute that. Then the main thing is I have to minimize this. Minimize this means you have to make this as a 0 1. So from this you can select what is your u, that is a control law. So if you want to choose this control law, then it should be R inverse B transpose P into X. And then this is based on Kx, where K equal to R inverse B transpose P. Okay. Then you have to do this also, X transpose uh, partial derivative of P with respect to T into X. So I think this is again okay. So here you have to substitute. So first you take this value from this, x transpose of px equal to this. Okay, so substitute that. So when you substitute this control law, then it becomes like this. So this is my final thing. So in this uh, this equation is called as Riccati equation. But you will understand once you implement this with any simulation software. But here these are the matrices P you have to concentrate on, and then R, Q. If you change these values, the other see, these are state vectors. B is the input vector. This you cannot change, but you can change P, you can change Q, you can change B and B transpose. If you keep on changing this, automatically the control law will be affected. Then if you give that control law to the given equation, the system will be controlled. So this is how your linear quadratic equal regulator works. Okay, so that's all for today. So with this, I'm finishing this process control course. In this course consists of 5 modules. So first module is process, second module is controllers, third module is actuators, fourth module is advanced control schemes, and sixth module is nonlinear systems. So in nonlinear systems, we have learned linear LQR also. And one more nonlinear controller is self-tuning regulator, which was already discussed in the fourth unit. So with this, I have finished this course. Thanks for your time and thanks for watching. All the best to everyone who watched this. Thank you.